Okay, Chemistry 3101, we said we were going to take a look at some problems that deal with infrared spectroscopy and mass spectrometry. So remember, spectroscopy is the interaction between matter and light, and spectrometry is the interaction between matter and energy. So starting with question number one, it says, which of the mass over charge values corresponds to the base peak in the following mass spectrum? Well, that's just a definition, and you should know that the base peak is nothing more than the tallest peak. Okay, it's the tallest peak in your spectrum. Okay, it has an intensity which is 100%. Okay, so you could put here intensity is 100%, and so the base peak is this one here. Okay, and you look at the scale. Okay, if you zoom in on it here, I mean, the only number that makes sense here is that it's just below 30, so it must be 29. So 29 would be our base peak for this one. The next question is about the exact same spectrum, but now it's asking us for which one is the molecular ion. So now we're looking for the molecular ion. Remember, we take our molecule, we hit it with a high energy beam of electrons, and we make a radical cation. And if it has the mass of the parent, that's our molecular ion. Well, if you take a look at the spectrum, okay, which number makes the most sense? Well, you can see that you have 44 and 45, which are on the far right-hand side of the spectrum. But you see that the peak at 45, okay, this is the one that comes from the carbon-13 isotope. This is the M+1 molecular ion, okay, which is only one, it just comes from the carbon-13. And so that one you can see is going to be the one at 45, right? It's right in the middle. And so this one here, this would be the molecular ion. All right. And so it must have a mass of 44. So 44 would be the molecular ion. And the other peak that's just to the right of it, a tiny little piece there, that would be from the M+1, which comes from the carbon-13 isotope, which, remember, carbon-13 is 1.1% abundant. Anyhow, let's move on from there. The next one just involves calculating some HDIs, and so you just need the formula for HDI. That's one way you could do it, or you could kind of look at the formula and try to figure it out another way. But this one, I would say you would need the HDI formula to do it. So let me just scribble the formula for HDI here. So HDI, or hydrogen deficiency index, or degrees of unsaturation, is 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens. Remember, the X stands for halogens. Okay, so fluorine, chlorine, bromine, and iodine. And so if we put our numbers in here, so let me get my blue pen again. So we say 1/2, 2 times the number of carbons, so that's 2 times 14, plus 2, plus the number of nitrogens, which is 2, subtract the number of hydrogens, which is 14, subtract the number of halogens, which is 0. You put all that into your calculator or into your brain, and when you're done, you end up with 9. So the HDI here is 9. So there's quite a bit of unsaturation in this compound. Now the next one is in the same vein, but I would say that the next one you do not need to use the formula. You can use the formula to solve this one, but if you look at the formula closely, it's C9. Actually, sorry, I misspoke. You do need the formula for this one. I thought it said C9H something different. I was misreading it. So we'll use the formula again. So we have HDI is equal to 1/2, 1/2, 2 times the number of carbons, which is 9, plus 2, plus the number of nitrogens, which is 1, subtract the number of hydrogens, which is 11, subtract the number of halogens, which is 0. There we go. I think I have it. So when you put that in your calculator, you end up with 1/2 times 10. So that gives you an HDI of 5, like that. Okay, there we go. So students are usually excellent at calculating degrees of unsaturation, or HDI. As long as they have the formula down pat, it's usually not any problem at all. So the next one says, what mass over charge values correspond to the molecular ion for the following compound? So remember, what we would do is if we put in the lone pairs here, okay, we would hit this with a high energy beam of electrons at 70 electron volts, or around 1600 kilocalories per mole, and we would end up making the radical cation. So again, what does that look like? it looks like this. We're going to have knocked off one electron. So we end up with something like this. And since we've knocked off an electron, it's going to have a positive charge. So that's our radical cation. So we lost one electron, but that doesn't affect the mass of the compound in any way, right? An electron is 2,000 times lighter than a proton or a neutron. So it's like nothing. It's like losing a piece of dust off of your body. You know, it doesn't change your mass. And so the formula of this compound is C6H14O. So if we tally that up for a carbon, we get 6 times 12, which gives us 72. For hydrogens, we have 14 times 1, which gives us 14. And then for our oxygen, we have 1 times 16, which gives us 16. If you tally all that up, you end up with 102. And so it's only got a charge of +1, so our mass over charge is going to be at 102. Keep in mind the nitrogen rule, right? There's no nitrogens in the compound, and so it definitely can't be E because that one has an odd mass. So we see the nitrogen rule is going to come up in question number 6. Which of the following compounds will have an odd value for its molecular ion? So remember, if you have an odd mass, okay, it means odd number of nitrogens. So we look at these, and the only one that has an odd number of nitrogens is number 2 because it has 1 nitrogen, which is an odd number. Number 3 has 2 nitrogens. That's an even number. And so that one would not provide an odd mass. So the answer is number 2. All right. I remember doing this question before with a class one time, and somebody raised their hand and said, "Is that all it is?" And I said, "Yeah, that's all it is." Okay, you just have to know odd number of nitrogens produces an odd mass, and that is referred to as the nitrogen rule. Okay, the nitrogen rule. All right, let's move on from there. The next one says, which of the following compounds shows the presence of bromine in it? And if you remember, bromine has two isotopes. So we have bromine 79, and then we have bromine 81, okay? And the relative abundances are 51% and 49%. So what does that mean? When we calculate the mass of our compound, we use bromine 79, but it's going to have, besides our molecular ion, we're going to have an M+2 molecular ion, which is going to be about as abundant as the parent. So again, the molecular ion will be about 51%, and the M+2 is going to be about 49%. And so the ratio, okay, so what's the take-home message, is the ratio of the molecular ion to the M+2 is going to be approximately 1 to 1. It's not exactly that, but it's close to 1 to 1. So remember, if we look at, let's say, if we zoom in on this one here, okay, it might be kind of hard to see in 4, but hopefully you can see the numbers here. I can read them. This is 20, 25, 45, 60, 70, 75, right? So this one goes up to 75. So what's the problem with this one? It cannot be this one, cannot be this. Right? Why? Because bromine has a mass of 79, and this only goes up to 75, so it cannot be number 4. So we can scratch that one off, and we can scratch 3 off for the exact same reason, right? It only goes up to 75, and so it cannot be this one. So I'll just copy and paste this over here and say it cannot be this one either. Oops, not what I meant to do. Not what I meant to do. There we go. Okay, so cannot be this one as well. Let's take a look at the first two. And if I look at number 2, okay, I can see the base peak, right? I have a big old base peak here, so base peak. And then I start looking to the right of it, and I don't see any 1-to-1 ratio of anything there. And it does go up to 90, but I don't see anything there with a 1-to-1 ratio. However, if I look at the spectrum for number 1, okay, here's our base peak. There's no arguing that, okay? This is our base peak. But then if we look to the right of it, we can see way above 125, we have 2 peaks here. And if you zoom in on those, you see that this is 1 mass unit and then 1, 2. So this would be our M+, and this would be our M+2. And you can see that the ratio is pretty close to 1 to 1. And so that indicates the presence of bromine. And so the answer is going to be 1, must have bromine in the compound. So I'll just circle this one here. There's bromine in that compound. Give me a thumbs up if you're with me on that one, now that I've gone through it. So recognizing the presence of bromine, or is there any questions about that one? Okay, because it's important that you recognize be able to recognize bromine and chlorine. Let's move on to this one. It says, which of the following compounds is consistent with the mass spectrum shown here? So let's take a look and see if we can find the molecular ion. And if we zoom in, we go from 70, 71, 72, 73. So this looks like the molecular ion to me. It has a mass over charge that is equal to 73. And then here, this tiny little nub, that would be our M+1. Now, if you're wondering, what the heck is this? You know, there's something here and something here. I think that that is just noise in the spectrum. So I don't think that has anything to do with the spectrum, because none of these compounds have a mass up around 120, okay? They're all in the like 75 range, okay? They're somewhere in that range. So I wouldn't worry about that. That's just noise in the spectrum. So somebody asked me, do you have to just remember the relative abundance of certain elements? Yes, there's two that you have to remember, okay? You have to remember that bromine gives you a molecular ion and M+2, okay, in a ratio of 1 to 1 approximately. And you have to remember the chlorine and its M+2 have a ratio of about 3 to 1. Okay, those are the two you have to remember. All right, so now that we see the parent for this one, the molecular ion has a mass over charge of 73, we see that it has an odd mass. And so we start looking through these compounds and see if we can find one that has an odd mass. And the only one is going to be D, because it has an odd number of nitrogens. It's this compound here. If we draw the compound, this is called diethylamine, but you guys know what an amine is, okay? And remember that I told you that the carbon that is attached to the nitrogen, that's called the alpha carbon, and that amines can undergo alpha cleavage. So if this compound was to undergo an alpha cleavage, so if it underwent alpha cleavage, it would lose a methyl group, so that would be M-15. So if we take 73, and we subtract 15 from that, we end up with 58. So we should see something with a mass over charge equal to 58. And then if you go on the mass spectrum, well, lo and behold, you have something right here, which has a mass over charge equal to 58. And so that peak, this one here, is from the loss of the methyl radical. And you would say that this is the result of alpha cleavage. Okay, it has nothing to do with the problem. It doesn't ask us to do it, but I thought you might want to take a look at that. The next one is kind of tricky. I'll walk you through it. It says, which of the following compounds is consistent with the mass spec shown below? And it says there's no molecular ion present. So we don't have a molecular ion for the compound. So that can make it tricky. However, one of the things that you can remember, if you have a good memory, would be when there's no molecular ion present, okay, you can say here, usually an alcohol. Okay, alcohols usually fragment so well that oftentimes you don't even see any molecular ion for the compound. And so based off of that information, I'm kind of giving away the answer that it must be B, because there's an alcohol in the compound, okay? But if we take a look at that compound, I'll just show you some further evidence. So this is called 2-butanol, and the name is neither here nor there. But if we take a look at these compounds, right, or this compound, we see that this is our alpha carbon, so we could have alpha cleavage here. So if we did that, then we would have M-15. And if we had our alpha cleavage here, then we'd lose an ethyl. We'd have M-29. Well, what's the mass of the compound? Well, the compound is C4H10O. So that means its mass is going to be 74. So let's see here. So yeah, its mass is 74. So I did that right. So if we have 74 minus 15, our alpha cleavage would give us a mass over charge equal to 59. And if we lose 29, we should see a mass over charge fragment. So if we take 74 and we subtract 29, we end up with 45. So let's see if we can see either of those. Well, you see the base peak is at 45. So this one here is mass over charge equal to 45. And so this is from loss of ethyl radical. And then you can see at 59, we have mass over charge is equal to 59. And so this is loss of methyl radical. I'll just write the structure in there like that. So there you go. And if you're wondering, what about loss of water? Well, if we take 74 minus 18, we would get 56. And it doesn't look like there's a strong peak at 56. And so I would say, maybe there just isn't a strong fragment for the loss of water for this compound. So that's kind of how you would do this one. But again, you would kind of have to have this information is when there's no molecular ion, oftentimes it's an alcohol because they just fragment so quickly. All right, the next one is a little bit more straightforward. It just says which one of the following compounds is consistent with this mass spec. So you can see the parent or the molecular ion is way over here. Okay, so it must be this peak right here. And so that has a mass. So this is the molecular ion. It has a mass over charge equal to 72. And then what I've done ahead of time, and so you would want to do this, is go through each one of these compounds. The first one is C5H12. And so that has a mass, I'll just put here, equal to 72 atomic mass units. The next one is C4H10O. We just worked this one out at 74. The next one has the same formula. It's C4H10O, which is 74. It can't be the next one because this one has an odd mass. So we'll put here odd mass. And so, again, this is one of those problems where sometimes students will say, is that all there is? Yes. Just find the molecular ion, find the compound that matches the mass. And so the answer for this one is A. All right. Let's take a look at number 11. Goes to 11. Which one of the following compounds is consistent with the mass spec? So, if we take a look at our molecular ion, hopefully this one will be kind of clear. You see the molecular ion is here. It has a mass over charge that's equal to 101. So that's an odd mass. And so we're going to look for something with an odd number of nitrogens. And so the answer is D. However, I would like to unpack this one a little bit. Let me see here. So what is the structure? So it's dipropylamine. So if we have 1, 2, 3, 1, 2, 3, like this. So this is the compound here. And like I said, so this compound is C6H15N. So it has a mass, over here, the molecular ion is equal to 101. And so if we do an alpha cleavage, so if this is our alpha carbon here, if we were to lose the ethyl, right, we would see, so if we have M minus 29, we should see something with a mass over charge, which is 101 minus 29, which gives us 72. So hey, what do you know? There it is. So we have 70, 71, and 72. So this is a mass over charge equal to 72. And so this peak is the result of alpha cleavage, and you could put here loss of ethyl radical or whatever. There you go. All right, so just one alpha cleavage we'll look at there. Let's switch gears and let's get into IR. So I'm going to ask you guys to help me with this one. I'll ask you a couple of questions here. So if I have this compound, it just says, what's the structure of this compound? So they gave us an IR. There are a few peaks in here that are interesting. So remember, it's always a good idea to draw a line at 3,000. So if this is 32, this is 28. So 28, 29, so this is 3,000, right around here. So 3,000 is around here. And then 1,500, Mr. Dion can't see. But anyhow, 1,500 is pretty close to that there. So that isolates the fingerprint region, and it helps us notice peaks that are in the spectrum. But let me ask you guys first, could anybody tell me what the HDI of this compound is? So if we have C3H3Cl as an HDI equal to what? Could anybody answer that, the HDI for this compound? And if you have to use the formula, on iPad. Yeah, so the HDI for this compound is 2. Thanks, Jennifer. Yep, thank you very much. So HDI is equal to 2. So what are our possibilities? If the HDI is equal to 2, we can either have 2 two double bonds. Two double bonds, that's one possibility. Another one would be one ring and one double bond. And there's one other possibility. Could anybody tell me what it is? So we could have two, oh, I guess we could have two rings. So two rings. Sorry, there's another possibility. Could anybody tell me what the other one is? So two double bonds, one ring, one double bond, two rings, or, yeah, thanks, Isaac. One triple. Okay. So let's take a look at our spectrum. I notice a couple of signals here. I notice there's one here, okay, and I notice there's one here that's above 1500. Okay, those seem to be the most interesting ones, right? This would just be sp3 hybridized carbon hydrogen stretching, so that's not all that interesting. But the one on the far left, okay, this one over here is the result of sp hybridized carbon hydrogen stretching from an alkyne, a terminal alkyne, right? Because you can see it's at 3300, right? If this is 3200, this is 3300. So that tells us that we have an alkyne. So that tells us if there's an alkyne, we must have a triple bond, and we must have this in our compound, right? Because this stretch, okay, comes from this bond here. Well, now I've used up two of the carbons and one of the hydrogens. There isn't much left, okay? Because this stretch here, which it's kind of hard to see, but it looks to me like it's around 2200 in that neighborhood for an alkyne. So this one is the carbon-carbon triple bond. So now this one, this stretch must be this. But again, we've used up two of the carbons and one of the hydrogens. All we have is one carbon left, two hydrogens, and a chlorine. So the only possibility is to add the carbon here, because you can't have a chlorine and then another bond to it, right? So it must be a carbon here, and then there's two hydrogens on it, and then we have the chlorine like this. So that must be the compound. So there we go. That's how you would solve that structure. Remember, if the formula only has three carbons in it, there's not a lot of possibilities, right? There aren't a lot of possibilities. So by looking at the IR, we were able to determine that we have this, right? From the IR, we figured out all of this. Okay, this came from the IR. And so the only possibility for the rest was for it to be CH2Cl. All right, next one. Oh boy. Anybody recognize any functional groups in 13? I bet you do. Yeah, thanks, Isaac. There's an alcohol in this compound, isn't there? Absolutely. I'll trace it out here, Isaac. So this is our strong. I'll put here OH stretch for an alcohol. It's not a carboxylic acid. We can tell that because the stretch isn't that broad. For an alcohol, it's between 32 and 3600 roughly. So that would be an alcohol for sure. Okay, so we've got that. Next question. I'll ask you guys. We'll kind of flesh this out here. If I have C7H8O, could anybody tell me what the HDI of this compound is? I'll give you a second to look at it. See if you can come up with an HDI. Yeah, thanks, Hannah. Yep, you're absolutely right. So Hannah solved it, and she said the HDI is 4 for the compound. Okay, actually, you all got it right. Thanks, you guys are great. Okay, so let me just share a little bit of wisdom with you guys, okay? At the level of chemistry 3101, okay, so in Chem 3101, and I'd say the lab as well, 3102, if you have an HDI greater than or equal to 4, almost always, I would say with greater than 99% certainty, okay, I'll just erase that, but it's almost always meaning that you're going to have an aromatic ring in your compound, right? Because an aromatic ring has one ring and then 2, 3, 4. So an aromatic ring has 4 units of unsaturation, okay? So again, HDI of 4, it's very rare that we would put 4 double bonds in a compound. That's pretty difficult to figure that out. But an aromatic ring, right, that covers the HDI. And then if there's an alcohol, right, we look at the formula, the aromatic ring gets rid of 6 of the carbons. So then you're only left with 1 carbon left over, okay? So let's do a couple more bits of work here with our IR, something that I neglected to do from the beginning, which was to draw a line at 3,000. So if that's 32, 30,000 is around here. So we'll draw a line here, and then we'll draw a line at 1,500. Oops, where did my ruler go? There it is. So 1,500 is around here. Okay. And I notice a couple of things here. I noticed that this must be an aromatic compound for three reasons, really. Remember I told you that the carbon-carbon double bond stretching for an aromatic ring, if you look at the handout, it just says 1,600, but I told you it's usually between 1,475 and 1,600. And you can see here that these stretches here must come from the carbon-carbon double bond stretching, okay, stretch, and I would add here aromatic stretching, okay? That's number one. Number two, if you remember the overtones, they were between 1667 and 2000 roughly. You see a bunch of signals here. So these are the overtones that we see with an aromatic ring, okay? And then the last one that I notice is that if we have an aromatic ring, we must have sp2 hybridized carbon-hydrogen stretching because we're not going to have 6 substituents on the ring. And so you can see that we have that right here, just to the left of 3,000. I'll put a line here. This is sp2 hybridized carbon-hydrogen stretching. And so we have an aromatic ring. And then I'd also point out that not everything must be aromatic because we also have some sp3 hybridized carbon-hydrogen stretching here. Okay, there's a little bit of it. So if we put that all together, what do we have? We have an aromatic ring. That gets rid of 6 of the carbons. We have sp3 carbon-hydrogen stretching. So that means we must have at least a methyl group, and we have a hydroxyl. So if you add that up, that covers everything, right? If we put all 3 of those together, we would have CH3 and then OH. Now I put them next to each other in the 1,2 position. If you put them in the 1,3 position, so if you put something like this, okay, like this, if you put, what is it, CH3 OH, or if you put it like this, with the methyl group at the top and the hydroxyl down at the bottom, I would accept any one of these. Now, if you're wondering, can I distinguish between these 3 using the IR? The answer is yes. You can determine it using the fingerprint region. However, it's not covered in chapter 14. It's covered in chapter 17 in the textbook, so I'm not going to worry about it right now. So I would accept any of these structures, okay? The actual structure is this one here, but I would accept this one too. I would give it 100% if somebody put that on their quiz. All right, let's move on to number 14, which just says match the IR spectra to the 5 C4H80 isomers. I'm going to do this one kind of quickly so we don't spend too much time on it. So you can see we've got an alcohol, we've got a ketone, we've got an ether with a double bond in it, we've got an alcohol with a double bond in it, and then we have an aldehyde. Okay, so I'm going to walk you through these. The first thing that I think we should look for are the alcohols, and you can probably tell that we have an alcohol here, right? And we have an alcohol here, okay? So the 2 alcohols are the cyclobutanol and then this alcohol here. Well, what's the difference between the 2 is one of them has a double bond. So we could look for the double bond, and we could also look for the sp2 hybridized carbon-hydrogen stretching. And so if we look at these 2, okay, you can clearly see which one has the double bond. If you go to the one at the very bottom, okay, we see that we have the double bond right here. So this is the carbon-carbon double bond stretching. And so if you look in here, it's kind of hard to see because I kind of covered it up with the OH, but this little bit here, okay, this thing here is the sp2 hybridized carbon-hydrogen stretching in your double bond. Let me retrace the alcohol here like this. So this is OH, and this one here is OH. And so based off of that, this one lacks the double bond, so this must be the cyclobutanol. And this one must be the one that has the alkene in it. Don't worry about the name of the compound. We haven't even talked about naming alcohols. That's not covered until organic chemistry too. But there we go. So we figured those ones out. Let's see here. So the next one, we have ketone. So we have 2 carbonyl compounds, right? This compound has a carbonyl in it, and this compound has a carbonyl. Carbonyls are around 1700-ish, I guess. So if we look at these, which two have peaks around 1700? It's going to be this one here is a carbonyl, and this one here is a carbonyl. If you look at this one and you think that that's a carbonyl, it's not. It's too low. Okay, it's not as high. So this one, you can see it's down around 1600, right? And our carbonyls for an aldehyde or a ketone would be above 1700. So you can see that this one is above 1700 and this one is above 1700. So now to distinguish between this one and this one, which one is the aldehyde and which one is the ketone, the way you do it is looking for the aldehydic carbon-hydrogen stretching, which comes out at 2750 and 2850, okay? We see weak stretches, okay? And I can see them right here. So this is the aldehydic, carbon-hydrogen stretching, okay? So this one must be the aldehyde, and so we'll put the aldehyde for this one here, okay? This is our carbonyl stretch here, and then the other one, the first one, must be the ketone, so we'll scribble the ketone here, and again, this must be the stretch here. All right, so we've covered those ones. So the last one must be the ether with the alkene in it, and if we take a look at that one, okay, we can see that for an alkene, we get our carbon-carbon double bond stretching around 1630. So if you zoom in here, if this is 1500, 1600, yes. So this must be the carbon-carbon double bond stretching of, we'll put here, I'll just write here alkene, like that. This one here, if you draw a line at 3000, okay, if we draw a line at 3000, then we see we have a peak here. That's weak. That must be the sp2 hybridized carbon-hydrogen stretching from our alkene. And then for an ether, we look for something, we look for a stretch around 1300 to 1000. So we have 1000 here, we have 1300, so 11, 12, 13. So this one here is the strongest one. So this must be the carbon-oxygen-carbon stretch of the ether. Okay, and so that must be the last compound, which is the ethyl vinyl ether. So I'll just scribble its structure here. So ethyl vinyl ether, which looks something like that. So there you go, kind of by process of elimination, we were able to solve all of those. So some take-home messages I would say for you guys here would be the aldehydic stretching. Use my yellow highlighter. Okay, aldehydic stretching, be sure that you are aware of that. Also, make sure you can recognize the difference between something like 1700 and then something that's at 1600. Don't mix up the two. An ether, right, is a strong stretch between 1000 and 1300. And yeah, there we go. So the last one says match the IR spectra to the compounds listed below. I'm actually missing oh, actually, no, I fixed it, okay? So there's a bunch of compounds on here. There's an alcohol. So this one is an alcohol. Then we have a nitrile. Then we have a ketone. We have a carboxylic acid. We have something reminiscent of the last one where we have an alcohol and an alkene in the same compound. We have a primary amide. We have an ester with an alkene. And then we have an alkyne. Okay, we have a lot of spectra here. Okay, but we can solve this pretty quickly. Okay, so let me just erase all that stuff that I put on here. Okay, so we have two so we have one carboxylic acid. If you look through all the spectra, kind of rifling through it, hopefully you can see that this one is the carboxylic acid. So this is the OH stretch, okay, of the carboxylic acid. So this one has to be the carboxylic acid. You can see it's got a carbonyl in there. So this is our carbonyl stretch here. And our carbon-oxygen stretch is actually this one right here. So that's our carboxylic acid. I'm not going to walk through every single stretch at this point, okay? So we figured out the carboxylic acid. That one's good. All right, let's look for some other low-hanging fruit. I see an alcohol here. So this one has an alcohol in it, and there's only one alcohol in the whole bunch. And so this one must be this compound here. This is called cyclohexanol. So we've got this one done, and we've got this one done. Oh, actually, there's another alcohol. Shoot. Where's the other alcohol? There it is. Okay, I noticed there's a difference between them. Okay, so this is an alcohol too. There's no doubt about that. But why is this the other alcohol? because this one, you can see it's got the sp2 hybridized carbon-hydrogen stretching, sp2 hybridized, and it also has the carbon-carbon double bond in it. Okay, so this is the carbon-carbon double bond like this, and this would be your carbon-oxygen stretching here. So this would be the compound that has the alcohol in it, and it's got the double, come on, and it's got the double bond in it like this. I noticed the one above it has a big old carbonyl in it, so it's got a big carbonyl in this compound, and there's nothing else in this one. So this one has to be the ketone because there's nothing else, there's no other stretches in there. The one above it, get a huge stretch here. This one is huge. I mean, let's zoom in on this. If this is 2000, 21, 22. So what gives you a huge stretch around 2000? Or, it's just above 2000. So this is actually a nitrile. So this is the carbon-nitrogen triple bond. So this is a nitrile stretch, okay? And there's one nitrile in the whole thing, and it's called benzonitrile because it's got an aromatic ring. And you notice that you've got your carbon-carbon double bonds, which are aromatic here. You've got the overtones. You've got, this is your sp2 hybridized carbon-hydrogen stretching in your aromatic ring. So this one must be this compound. This compound is called benzonitrile. So that's that one. So we've got all those done. What's this one here? This one also has a carbonyl in it. So this one has a carbonyl, but this one's kind of interesting because it's got this broad stretching here, but it's not a carboxylic acid. So if you think about where else would I get broad stretching from, it would be from this NH2 group, right? Because it can participate in hydrogen bonding. And so this would be the primary, or the NH2 portion, right? Because it can have symmetric and asymmetric stretching. And then you also see that you have your carbon-carbon double bonds from your aromatic ring. So aromatic. You can see, so I don't even know if you can see the sp2 hybridized carbon-hydrogen stretching. It's kind of buried in there. But the only possibility for this compound would be the aromatic ring with the amide, like this. Have we solved them all? No, there's two left. Okay, so this one, the top one, has to be an alkyne because you can see you have an sp hybridized carbon-hydrogen stretch here, so it must be this compound, okay? And you can also see a tiny little nub here for the carbon-carbon triple bond for that one. And then I guess we've got one compound left. Which one is it? Oh, it's the ester. Okay, the ester with the double bond in it. So this one has to be this compound. So let me just put the structure in here. It looks like this. And then we have a double bond over here. So let's see if we can find all the pieces here. You can see the carbonyl. Okay, so we get a big old carbonyl stretch here. But then we also have the carbon-carbon double bond stretch, which is here. We have the carbon-oxygen stretch, which is really pronounced in an ester. And then the last thing I would say is you have your sp2 hybridized carbon-hydrogen stretching, which is in here. And so you can identify all the parts of this ester. So that's kind of how you walk through some IR and some mass spec problems. I hope you found this useful. And remember that in the announcements that I posted another problem, another set of problems that I solve on my YouTube channel. You'll notice that there's some problems here at the end. I'm not going to go over these ones right now because these just come from the textbook, and you have the solutions to all of those in the solutions manual. All right.